Thank you. Now we will move on to the QAOA section of this session with two talks about the optimal QAOA design. One about for max-cut problems and the other will be for traveling salesman problem. And the first speaker is Bence and Bakó, and judging on the excellent co-authors, it has to be some very interesting results. So please, Bence, the stage is yours.
Thank you. Hello, everyone. Thank you for the introduction, Zoltan. And I also want to thank the organizers for this great event and for this opportunity. Now I will talk about a relatively new approach for QAOA and how it specifically applied for the max K-cut problem. But this idea is quite generic, and in the next talk by Adam, you can hear about a more complex problem as well. But first, very briefly, let's see what QAOA is. So it's a variational quantum algorithm for combinatorial optimization. So basically, it uses trotterized adiabatic evolution to get from the ground state of the mixer Hamiltonian to the ground state of the problem Hamiltonian. For this, we apply, first we prepare the circuit in the ground state of the mixer. Then we apply the unitary generated by the problem Hamiltonian for some gamma 1 time, then the same for the mixer Hamiltonian, and we do this procedure p times, where p is the number of layers in the circuit. Now at the end, if we measure in the computational basis, then we get a bit string that solves our problem of interest. These problems are usually formulated as quadratic unconstrained binary optimization or QUBO problems, which then with this simple transformation can be embedded into the ground state problem of an Ising Hamiltonian of this form. So usually we have two local Ising Hamiltonians. Now I will show you certain improvements or certain new variations of this algorithm, and in the meantime I will try to introduce some quality measures which we should consider when designing such an algorithm. But first, let's see our problem of interest, which is the max K-cut problem. Now, given a graph with n vertices, we want to color it with K colors, let's say. And the goal is to maximize the number of edges connecting different colors, or in a weighted graph, to maximize the sum of weights of edges connecting different colors. Now, if we look at this simple example of a graph with 5 nodes, then one optimal coloring would be the 0th node in the colored with the first color, then 2, 3 with the second one, and 1, 4 with the third one. Now, to formulate this problem as a quadratic problem, we need to represent our nodes with in the one-hot representation, meaning that we assign k bits or qubits to each vertex. And if the vertex is colored with the first color, then the first bit or qubit is 1, the others are 0, and so on. So we can use this representation to formulate an equivalent problem to this max K-cut, which in turn tries to minimize the number of edges the number of edges connecting nodes colored with the same color. So in this formulation, the first term penalizes if we have assigned, let's say, multiple colors to a node, or if we have assigned no color. So if we have all zeros, or if not only one bit is 1, then we have a penalty term here with some constant factor. And then the second term penalizes edges connecting nodes with the color with the same color. Now, in the simplest version of QAOA, we use this one-hot representation and the corresponding QUBO formulation to construct our problem Hamiltonian. And we use a simple X mixer, which is simply the sum of Pauli X matrices over all qubits, which then can be exponentialized and implemented as Rx rotations with some beta parameter over all the qubits. Now the ground state of this mixer is the plus state, so we can achieve this by applying Hadamard gates over all qubits. Now this is the most simple version of QAOA for this problem. Natural extension of it is quantum alternating operator ansatz, from which we consider the XY QAOA, which also uses one-hot representation, so n times k qubits, but with a good mixer, this XY mixer, and by preparing the state in the superposition of only one-hot states, we can reduce the subspace in which the evolution takes time to this superposition of only one-hot states on each register. So in this case, we can also remove the penalty term from the cost function because we here only have one-hot states. And then we can use this XY mixer, in which case we can, how we choose this K and K prime, where there are multiple approaches, but let's consider the ring mixer, in which case K prime is K plus 1. And so we get this linear connections. And at the end, we also connect the last one with the first. So we have this ring structure in the mixer. So in this case, we introduced our first quality metric, which is the size of the effective space in which the evolution takes time, and in which we can find the optimal solution for the problem. So in the original QAOA, this was the whole Hilbert space of n times k qubits, but in this case, it was reduced to only n log k. So we have our first quality measure. Let's introduce another one, which is the number of physical qubits, which we want to keep as low as possible, while still having these near-term devices of not so many qubits, let's say. One thing we can do is change our representation from one-hot to binary, in which case, if a vertex is colored with the first color, then it should be in the 0-0 state. And with this technique, we can reduce the number of qubits to the order of n log k. Now, one approach which utilizes this encoding change is the HOBO, or higher order binary optimization, in which case, in our problem Hamiltonian, we have two parts. The first part checks if we have a valid coloring, meaning that if we have, let's say, 3 colors, then and we need then 2 qubits per register, then the state 1-1 is not a valid color, so we should penalize it somehow. The second part then is responsible for this penalty for edges connecting vertices from the same color. But then in this part of or basically in both parts of the Hamiltonian, we have not only 2 local, but higher order interactions. And there are multiple ways to implement these. Let's say if we have a Z-Z-Z interaction, then it can be implemented with 4 CNOT gates and Z rotation. But there is a more efficient way in this simplified circuit. We consider all 1, 2, 3 body terms in a 3 qubit scenario with only this many CNOTs. And in this case, we also use this simple X mixer for the mixer Hamiltonian. Now, with this in mind, let's consider a minimal example. Let's say we have this Boolean function, which is equivalent to the AND operation over all bits. Now, if we use the usual transformation to get an Ising Hamiltonian, then we can see that the number of terms in the Hamiltonian is exponential. So for this reason, let's introduce our third quality metric, which is the number of gates. So if we use this polywise implementation of HOBO, then the number of gates is also exponential. However, there is an alternative approach. So instead of or implementing each Pauli term separately, we can use a so-called simulation technique, in which case we just simulate the behavior of this circuit somehow. And with this approach, we can reduce the number of gates to the order of n squared. And now the question is, can this approach help our problem in the QAOA framework? There has already been a version of QAOA which uses basically this simulation technique, which is by Fuchs and colleagues, which we call Fuchs QAOA. And it also uses binary encoding with this simulated approach. And then it applies additional circuits for fixing the incorrectly assumed different colors. So let's say if we have the max 3-cut problem, then first we apply the max 4-cut because here in the objective phase we need k to be a power of 2. Then we have to apply the fixing phase for the states 2 tensor 3 and 3 tensor 2 in the case of 2 vertices, let's say, because if we only have 3 colors, then 0, 1, 2 are the valid ones, and 2 and 3 should mean the same things. So we need a fixing for this. Now, both of these techniques, so Fuchs and HOBO, by using this binary representation, they increase the depth. So this transition comes with a trade-off. So for this reason, let's consider an additional quality measure, which is the depth, and for which we consider the 2 extreme cases. First, the all-to-all topology, so when each qubit is connected to every other one, and the linear nearest neighbors topology. And we always measure the circuit depth with only 1 and 2 qubit gates. So everything should be transpiled to only 1 and 2 qubit gates. And now if we look at the scaling this is meant in a big O notation, then if we look at the scaling, then we can see that Fuchs QAOA uses this simulated approach, but due to the fixing phase, the scaling is rather bad. So how can we improve it to really benefit from this simulated approach? And if we look at the implementation, and we tested numerically how these metrics scale, then we can see that if the number of colors is a power of 2, then Fuchs is quite good, but otherwise it scales really badly. So what we did was we tried to get rid of the fixing phase of Fuchs completely. And how we could do this was to start in the superposition of the first k numbers in binary representation. So for 3 colors, we would start in the superposition 0, 0, 0, 1, and 1, 0. And if we have an implementation of such a state preparation, then we can use the Grover mixer for our mixer Hamiltonian, and which is basically just composed of the inverse of the state preparation, some X gates, a multi-controlled Z rotation, and uncomputing the X gates and the inverse of the state preparation. And we do this over all all the registers. So all of these can be done in parallel. So basically, the efficiency of this of our implementation of this SIM-QAOA comes down to the implementation of the state preparation and of multi-controlled Toffoli gates, basically. And now if we look at the scaling of these quality metrics, we can see that in all of them, it reaches a near optimal values, and it reaches the lowest of all in the depth on LNN and in the number of gates. And if we look at the implementation as well, and let's remove Fuchs QAOA for now, then we can see that indeed in the number of gates it is the best one, and on depth on LNN topology it also reaches the best result in just under 50 colors. And we could keep the number of qubits in the same order as for HOBO. Now, what I should mention is that all of these implementations were done in Qiskit, and we made a separate version for LNN topology. So we didn't use the transpiler to transpile it to LNN, but we made separate versions. And at the end, we did transpile them to use only general 1 qubit gates and C0 gates, and we measured the number of 1 and 2 qubit gates, so general 1 qubit gates and C0 gates, and the depth for these transpiled circuits. So now the question arises, can this idea be extended to more complex problems? And in the next talk, you can hear such a scenario by Adam for the traveling salesman problem. So thank you.
Thanks a lot for this great talk and for keeping the time very well. At this stage, there are no questions, and I guess also on Discord there are no questions. So I will ask a question. So you said that I mean this method is you showed it for the traveling salesman problem, and the next we will or Adam will talk about the sorry, you showed it for the coloring problem or max K-cut problem, and Adam will talk about the traveling salesman problem. So this is in general usable for various combinatorial optimization problems. Have you thought about using it for other type of variational optimization algorithms, the simulation method, for example, for many-body physics or quantum chemistry, or that's a too far-fetched question?
Well, honestly, I haven't thought about it yet, but to me, it does sound interesting. I don't know. Maybe we should consider such scenarios. Okay,
thanks. I completely agree because it looks very general. Okay, so what about the different I mean, then I ask a second question until somebody is asking. So what about the different optimization scenarios? So you talked about the max K-cut, now comes the TSP. What else will it be useful for? Can you say a few other, let's say, optimization problems?
Well, I believe we also have an implementation for the set cover, I believe. And this idea may be most beneficial for constrained problems, I think.
When you have an extra constraint on
Mhm.
like, yeah, exactly. I agree with that. Okay, thanks a lot, Bence. It was a very nice and clean talk. Thanks a lot.
Thank you.
Other people are saying also that it's a great talk. Thanks. I stopped the recording.